to talk about another circuit that has both a independent voltage source as well as a voltage controlled current source. And just kind of look at how you kind of think about this analysis. And so when you take a look at a very simple circuit like the one we have here, and you might go, well, this should be straightforward, except that when you start to look at this structure, all of a sudden you go, ooh, okay, that's not going to make the circuit quite as easy. So how do you approach a circuit like this? Well, one of the things you notice is that this voltage V1 is right here, so it makes it very straightforward in terms of how you analyze that piece of it. By the way, this is not a contrived circuit. This is actually something that would be, you would expect if I had a common gate circuit where the source is the input. So, and I have two different resistors, R1 and R2. So how would this go? Well, the solution to making this be fairly straightforward is you realize you have the one node up here to play with. And you know that you've got KCL at that node, which basically means that all the current going in has to equal the current going out. So you just simply add up all the currents. This one, the current that's going from V1 to V2, that's why you end up getting V1 minus V2 equals to the current that goes through R2. That's V2 over R2. And so you start there and you think, okay, that gives me an equation. And by the way, that gives me able to give me V2, which in this case would be the output, as a function of an input voltage, which by the way could be a static voltage or it could be a time varying voltage. Nothing is necessarily certain in that situation. So then you put this together and what you realize is I've got, I can sort of reorganize. I get GS plus 1 over R1. And then I get these two different terms for V2. Well, notice that this sum 1 over R1 and 1 over R2 is a parallel combination of R1 and R2. So that instinct that you think that these two is a parallel combination is probably not too far off. And so as a result, this becomes your expression, and then you can actually solve for V2 as a function of V1, which is of course your input source, of a form like this. You think this is great, and now I should just be done, and I could plug in numbers and finish. And you could do that, and that's fair. Imagine I have these as my values, which would be not surprising values for particular bias conditions. So for both GS, R1, and R2, but notice a couple things. One place I've got GS, and I've got 1 over R1. GS is 1 over 100 ohms. 1 over R1 is 1 over 200 kiloohms. The GS is going to be much, much larger than this term. So it would be fair to just neglect this term. And in most cases, that would probably be fine. The other thing is I have R1 and R2, and notice that in a parallel operator, it's always the smallest one. When the one is much, much bigger than the other, it's the smallest one that is basically what comes out of this. So I've got R1 parallel R2, that basically means I just get the R2 value there. And so the nice thing is I can kind of make these two approximations, and the result kind of follows along very nice along the line of V2 GS R2 V1. Given these values, just plug them in. I'm going to get a result where V2 is going to be just 200 times V1, whether that's a static signal, whether that's a changing signal. And so one could plug in a value of V1 to be a millivolt, and you would get V2 would be 200 millivolts, and so on. And so you can kind of work through this, but you can see that even though I've got a dependent source in here, this really isn't necessarily all that scary or that difficult.